This is the second video in section 15.6, triple integrals. I want to pick up here with a couple notes, a couple of things to help us think a little bit more about these triple integrals, and then see a couple of examples. So first, I just want to note that last time, in the last video, we left off by saying that the volume of a region E is equal to the triple integral dV. Well, so you might be thinking, well, if I can't ever put a function in here and get something meaningful out like a volume, then what are these things used for? Why do we need these triple integrals? So let's see a couple of reasons we might care about these things. First of all, one nice application is given a region E, 3D solid region E, with mass density, we'll call this Greek letter rho of x, y, z, at any point x, y, z in the region. So given a region E, if we know the mass density, which is really just mass per volume, right? That's like kilograms per cubic meter, something like that, for example. This is a mass per volume. If we know the mass density at every point inside some region, then the total mass of the entire region, E, is given by the mass of E equals the triple integral of this mass density function rho. So it's saying it's like at every point inside of E, I am taking the density there and multiplying it by a little infinitesimal piece of volume. Density times volume is just a little infinitesimal piece of mass, right? So it's like we're getting a little amount of mass dm and adding it up over every little point inside of E to get the total mass of E, m of E. So that's one nice application. If I know the mass density of a region, I can find its total mass by taking a triple integral of that mass density function over the region. Kind of related to that is the idea of center of mass. And we won't go through a lot of the derivation here, but it's nice to know we have formulas that give us important quantities involving formulas involving triple integrals that give us important quantities. So for example, the center of mass of a solid region E, the center of mass is a point x bar. Let me erase these, sorry. X bar, y bar, z bar. So it's a set of coordinates, it's a position in space given by these formulas. X bar equals the triple integral over E of x times the density dV, all divided by the mass. Similar for y bar. It's y times the density, all over the mass. And z bar similar. So the way I like to think about these is that the center of mass is really just a weighted average of all the x coordinates inside this E value, this E region, where the weights in that weighted average are given by the density. A more highly dense area will have the x value attached to it there, kind of be weighted more heavily towards this overall sum of all the x values, and then we divide by those masses. If you think really hard about this, this looks a lot like just taking a weighted average. Add up a bunch of values times some weights given by here, the density, then divide off the sum of all those densities, which is just mass. Sorry, I wasn't happy with my integral signs there. A little better. So anyway, these are nice formulas we can use. Again, I'm not going through much of the derivation other than just to say that these are sort of like the x bar is a weighted average of all the x coordinates inside of E, where the weight in that weighted average is given by this density, the mass density. So you might see that as a nice application. You can find the center of mass of an object. You can find other things related to physics, things like moments and second moments. But we will go through those here. So I just want to do a couple simple examples of triple integrals, not even using those applications necessarily, just seeing some more examples, getting us familiar with triple integrals. This example says sketch the solid whose volume is given by this triple integral. Right, since we know we have only dv here, there's no function out in front. It's like there's a function 1. And so we know this is like the triple integral of just dv over some region E. So the triple integral should be the volume of that region. We want to sketch that region E. So let's see if we can figure this out. I want to remember how we thought about putting these together to see about how we can kind of take them back apart. Let's see what we can do. I'm not happy with the direction of that axis. Maybe that's better. Okay. So let's look at this. We are saying, let's take a look at this integral here. We have 0 to 2, 0 to the square root of 4 minus y squared. And then remember, we want to think of that inner integral as being inside of a double integral over sort of the footprint of this solid region E. So I'm going to think of this inner integral separate from the outer two integrations that make a double integral. Sorry about that, took a second there. So here I want to think of my double integral as being in the, being over a region in the yz plane, because my last two differentials are y and z. So whatever solid region I have, I'm thinking of projecting it back into the yz plane here, right? Back into the yz plane. So let's see what happens when I try to do this. Well, I'm really trying to sketch this kind of footprint region, right? This D region, which is given by these integral bounds, which are saying that the y value goes from 0 to 2. So the y value is from 0 to 2. Right? 0 to 2. And that's, I'm just thinking in the yz plane here. Right? Maybe you do a picture of the yz plane over on the side, but I'm just thinking of it here. And then we know that the y values are going up, the z values here are going from 0, so from z equals 0. Where do they stop though? Right? On the y-axis here in the yz plane, that's where z is 0. Where do they stop? You know, to make this clearer, let's just do this in the yz plane. The y we said goes from 0 to 2. And the z's go from z equals 0 up how high? Let's see, they go until they get to this upper z integral bound, z equals the square root of 4 minus y squared. So square both sides, and you see this is really just this circle of radius 2 centered at the origin in this yz plane over here. But we know y is only going from 0 to 2, and our z values are starting at 0 and going up, so we must only have the top quarter of this circle. Since y is from 0 to 2, we won't get anything over here. And since the z values are starting at 0 and going up to this equation, we know we're not going to get anything down here, nothing below. So let's see what we do get. We get z-values going from 0 up to this quarter circle. Right. So translating that picture over here, in the YZ plane, our footprint really just looks like this region, which I'm going to draw pretty thick here. Right? That is our footprint. That is that region D. Let me clear it out. Draw it a little better. Right, it's a quarter disk. That's our region D that we were describing over here. So that's just the footprint of this 3D solid. It's the footprint of it if we think of projecting or shining light perpendicular, parallel down the x-axis at our solid object. We knew somehow we're landing, our entire object is landing in this footprint here. Right. So let's see what our object actually looks like by looking at the inner integral, that x integration. Let's see what it looks like. Well, notice, maybe I'll come over to the side here a little bit. Notice here that inner integration is saying that x starts at 0 and goes up to 2 plus root y squared plus z squared. So x equals 0, that's just saying in the yz plane, right? Our x values are starting in the yz plane and they're going forward out of the page into the x direction. But how far? What surface is stopping them? It's this x equals 2 plus root y squared plus z squared. That is the surface that is stopping the x values. That's the upper bound on the x values. So we need to see what this graph looks like. This is really x minus 2 equals the root. And we square both sides. And we see this is just a shifted cone. Right, this is a cone running along the x-axis. And we can say it's shifted 2 units oh, I need to change one little thing if you don't mind. I need to make this a negative. I am sorry. That's got to change to a negative. I'm going to change that to a negative. I don't think I can erase nicely, so I'm just going to put a negative there. Okay. So when we now look at it with a negative here, it really doesn't change anything up to this point because we squared and got rid of that negative. But we'll see. I actually do want a negative on that for what comes next. But this is a cone shifted 2 units in the positive x direction. And since we had the negative sign up here, wink wink, I changed it to a negative. But since we have that negative sign, the negative says, the negative, I should say, implies that the cone opens, we're only getting a half a cone, and the cone opens in the negative direction. That's why I wanted that negative there. I want this cone to open in the negative x direction. So let's go back and change those notes and think of having a negative here all along. Okay, so we know this is a cone opening in the negative x direction, but it's already shifted from the origin 2 units in the positive x direction. So I want to see if we can get a rough little sketch of it down here. This cone looks like, maybe a little broader, looks like this. Right, it's opening along the x-axis in the negative x direction. So if now I go back over here, remember this was shifted 1, 2 units forward in the x direction. If I go back over here and draw it, I'm going to be interested in, well, if I go 2 units forward, maybe that's the 2 units forward mark, and I start drawing this cone, right? It needs to just keep the part that sits over this quarter disk, over the quarter disk D. So we need to know, does the cone, when it gets to the XY plane, is it the YZ plane, is it lining up with the edge of this quarter disk D? Or is it maybe coming out a little wider, a little narrower? How are we going to work this out? Well, in this case, notice when I take this equation for my cone, this equation over here, if I plug in x is 0, that would be where this thing is, where the cone's intersecting the YZ plane, when x is 0. It implies we get the equation y squared plus z squared equals 4, which matches our footprint exactly. So we know this cone is coming down, and the trace of it in the YZ plane is actually just the edge of that disk D. And there we have it. There we have our solid object. This is a cone, but we're only keeping 1/4 vertical slice of it. And this is a little semicircle down, little quarter disc down here. And the cone has been split into 4 pieces along the x-axis. We're only keeping this one in the first quadrant. Right, so that's our solid object. It's a quarter, it's a vertically split quarter of a half cone. Right, half cone because what we specified over here, we're only getting the negative opening half, not the positive opening half. Sorry for my work being kind of all over the place here. I hope you were able to follow it nonetheless. Let's do this last problem down here, in case you need another look up here. This is essentially it. Let's take a look at this last problem down here. Find the volume between the paraboloids. And I think this problem is a really great segue into the next section, which is triple integrals in a new coordinate system called cylindrical coordinates. But this is going to be a good bridge into that world. So I want to find the volume between these paraboloids. All I need to do is set up a triple integral over this volume, whatever it looks like, over this solid region between the paraboloids, and integrate dv over it. We know that equals the volume of the region E. So let's let E be the region and say we're going to evaluate the triple integral over E of dv. Well, again, we better figure out what this thing looks like. Let's do it with some pictures here. We're already told these are paraboloids. This one is opening along the positive y direction. Something like that. And the other one is shifted 8 units in the y direction and then opening in the negative y direction. So if this is 8 units, it's doing something like this. It's opening in the opposite direction. And notice by the symmetry of these are both circular paraboloids because they have the same coefficients on their squared terms. So there's no eccentricity to speak of here. That means when they intersect, they're going to intersect in sort of a, not sort of, exactly a circle. In fact, let me redo that intersection in a different color so we can make it pop a little bit. Let me do that in red. So wherever those paraboloids intersect, right, they have the same axis and they're both circular, so they're going to intersect in a circle. I'll say circle of intersection. So if we want to find the volume between these two things, what we really need to do is figure out if this is my shaded region E. Let's not overuse the red. If all this stuff in between these two paraboloids, if that's E, then what I need to do is figure out a way to project this solid region into one of the coordinate planes, either the YZ coordinate plane, so kind of back into the screen, the XZ coordinate plane, so towards the left, or the XY coordinate plane, so downward. Notice that the brim of this shape is formed by this curve of intersection, this circle of intersection. So if I was thinking of projecting this way back onto the XZ plane, then the shadow or the footprint of my entire solid object E is going to be defined just by that outer brim in red, right? That curve of intersection. It's going to look something like this. Let me clean up this. We don't need to see the edge of this paraboloid out here that we're not using. If anything, I'll even just bring it out further, out of our way. Right, so I think I overshot this a little bit. Right, so whatever circle this is in red, when you project it onto the XZ, that's going to form our footprint in the XZ plane. So I want to draw that out, make sure I'm very comfortable with what that footprint looks like. Should be a perfect disk, but it's okay if it's a little off. Well, that thing's radius is what we need, so we can, just so we know what this curve really looks like, how to describe it with an equation. So I need to find that circle of intersection since its radius is really defining the radius of my footprint. So let's do that intersection down here. Maybe I'll do that in red. That intersection is just where y equals x squared plus z squared and y equals 8 minus x squared minus z squared. Let me just, remember I want to know what the xz picture is, so let me just equate these two things that equal y. Well, they both equal the same y, so let's equate them to each other instead. That's a transitive property of equality. Add the stuff on the right back over to the left side, and you get 2x squared plus 2z squared equals 8, which is x squared plus z squared equals 4. Circle centered at the origin, radius 2. So now we know everything about this circle. We know it has radius 2, which lets us write the equation of this thing. We actually have that down here. We have the equation of that footprint. So all we need to do, and maybe notice, first of all, that, let's say it this way. Let's get back to that here in a minute. This integral we started with, we're going to start by thinking of the double integral over that footprint, right? dv, we're just going to think of as a triple integral, so a double integral over the footprint, and that leaves, remember that footprint's in the xz plane, so that leaves the y integration left to do inside. So we need to figure out bounds on all three of these integrals. How do we describe the footprint? Well, that's actually not too bad. The footprint has a radius of, it's a circle of radius 4, so it goes from -2 to 2 in the x direction. I could write that down. That's in the x direction. The other part of the footprint is the z. That goes from z equals negative this root up to positive this root, right? So we have to solve for z over here and see that each leg of that, each branch of that circle is just a positive and negative root of this equation here. So I'll say z goes from negative that root, the bottom half of the circle, to positive that root, the top half of the circle. That's our outer two integral variables done. We just need to figure out now what to do with the y. Well, looking at our region here, the y value, right, we want to subtract top surface minus bottom surface, or go from, maybe is a better way to think of it, where our y values start to where they end at all the xz in our footprint D. They start on the rightward opening paraboloid, and they end when they get to the leftward opening paraboloid. Right? I'm drawing a bunch of different arrows representing where the y values start on the rightward opening paraboloid and end on the leftward opening paraboloid. So let's just write that. What is our y value on the rightward opening paraboloid where we start? That's this guy up here. That's x squared plus z squared. That's what y equals on the starting position, the rightward opening paraboloid. The other one is where we end. That has a y value given here. Make some space. Right? So overall, we have our integral. All we need to do is somehow evaluate this big ugly mess. From negative 2 to 2, from negative root 4 minus x squared to positive root 4 minus x squared. That covers the footprint, the circle, the disk I should say. And then finally from x squared plus z squared to 8 minus x squared minus z squared. dy dz dx. That's our integral. If we can compute that thing, just working from the inside out, doing partial integration, we'd be in good shape. But I claim that this is the absolute worst way to find this volume. Because notice, all we're doing from this step up here is somehow expressing that footprint in terms of x and z integral bounds. So why don't we instead express that footprint, which is a nice polar rectangle, right? Our footprint's a nice disk, which is an easy polar representation in a double integral. Let's express, let's say, or we could express that double integral as going from 0 to 2 pi, and the radius 0 to 2, the radius of the circle. And then we'll just say the inner integral is what z used to be when we did polar coordinates. But now we're kind of letting the x and z play the role of the polar coordinates because we have our disk in the xz plane, and y is like that third variable. And when we did polar coordinates, we just described things in the plane. Well, we can do that in any plane, not just the xy, but the xz, and then let y be as it usually is. So let's just think of it this way. Oops, do this here. Let's convert everything to polar, where z and y have kind of changed places now. Oops. Instead of y equaling r sine theta, that's now a z value taking its role to express things in the xz plane. So these guys are saying that our x and z have turned into r theta polar variables. So the dA better turn into the polar form of dA, which is r d theta. Need that extra copy of r. And inside here, we just need to convert these expressions to polar. X squared plus z squared, where z is what the usual y is in polar, this gives r squared. 8 minus x squared minus z squared, this is 8 minus r squared in polar. And the dy we'll just leave as a dy. Right? That's still our usual variable. We didn't do anything to this inner integral. We just played with that area integral by doing it in polar. And look how much easier this is. This gives us the integral from 0 to 2 pi, integral from 0 to 2, integral from r squared to 8 minus r squared of r dy, putting that r past all the differentials, d theta. Notice how much easier this looks than this terrible expression in rectangular that we already came up with. This is pretty easy to actually compute fully. That one's not too bad at all. You can choose what you would prefer to do. I bet you'd rather do this one. So I'm not going to do all of it though, but I want to notice how much I can separate this too. The theta integration I've written last, there is no mention of theta inside of that theta integral. Let's pull all that stuff out. Of the theta integral, leaving just 0 to 2 pi d theta, which is just 2 pi. And now we could start working on this integral if we wanted. Maybe I go ahead and do the y integration here. The y integration sees this copy of r as just like a constant here, so that just hangs out. And then I actually integrate dy to get y evaluated from top to bottom. Y equals r squared to y equals 8 minus r squared. And this is still inside of an r integral. So if you work this out, it looks like we would have 8r minus r cubed minus r cubed, I believe. And dr slipped in there. So I'll let you finish this from here. This is an easy Calc 1 integral. But I hope we see how we, from thinking of these triple integrals as just a double integral over a footprint of a single integral inside, that allows us to actually express that double integral in polar coordinates if it's more convenient, which it certainly was here. Our disc-shaped footprint there made it very convenient to express this dA and the double integration in polar variables. Doing exactly this, replacing any two of your variables with polar variables and leaving the third unchanged, is exactly what we mean when we talk about, be careful, cylindrical coordinates. We take two polar variables in 3D and leave one variable in rectangular, usually z. So that's exactly what we've done. We have secretly converted this to cylindrical coordinates, even though we haven't learned that yet, and computed it in a much simpler way in that system. So we'll see more about this cylindrical coordinates in the next video, but that is it for this one.